Hello everybody, welcome to the 2021 Beale Lecture. Thanks for joining us today. I'm Gavin Blackett, the Executive Director at the OR Society. Just going to start with some housekeeping stuff. And if you've been with us through our many virtual events through the last 12 months or so, you'll be well familiar with them. Just so that you can see the slides that we're going to be using this afternoon, we suggest you position the speaker box in the top right-hand corner of your screen. Please use the chat function to send us any messages rather than raising your hand. But if you have any questions for either the speaker or the panel that we've got lined up today, submit them using the Q&A function. And you can upvote your favorite questions there so they get to the top of the order when we come to be asking them. Both elements of today's sessions will include time for questions after the presentations. The final thing is that this session is being recorded and should be available shortly after the event via our website. So I'll now hand over to Professor Edmund Burke, who's the President of the OR Society.
Thank you, Gavin. Thank you very much, and welcome everyone to the 2021 Beale Lecture. I'm really delighted to be hosting this event. It's the very first time that this event has been held online, and I seem to have been saying that quite a lot over the last few months for various OR Society events. It feels as though it's a lot longer than 12 months since I was welcoming everyone in person at the Royal Society for the 2019 event. A lot has happened in those intervening 12 months. And although this is the first online event, it is traditional that we have it in two parts, and that tradition is being upheld today. So I'll speak about our headline event a little later, but we will start today's event with a talk from Dr. Geraint Palmer, who is a lecturer at the University of Cardiff. Geraint won our Doctoral Award for 2018, and he's going to be talking about the subject of his doctoral research, Modelling Deadlock in Queuing Systems. Geraint will talk for about 20 minutes, and there'll be an opportunity for questions, and then we will move on to the panel for this Beale Lecture. So, Geraint, over to you.
Thank you very much. I'm going to share my screen so that I can show you my slides. So, can everyone see my slides?
Yeah, I can see them.
Thank you very much. So, yeah, I'm Geraint Palmer. I'm currently a Welsh medium lecturer at the School of Maths in Cardiff University. And I'm here to talk about what I did during my PhD. And I did my PhD with two great supervisors who are now two awesome colleagues, Paul Harper and Vince Knight. And the title of my PhD thesis was Modelling Deadlock in Queuing Systems. But I think that only really sums up a small part of my PhD. The running theme throughout it was a piece of software that I wrote in order to conduct all my work in my PhD called Q. And I'm going to talk more about that today. So back when I started my PhD, I knew that I was going to be doing work with discrete event simulation. And the other thing I knew was that I knew all my work was going to be as reproducible as possible. And I hope I've achieved that. What that means is that I was hoping that someone could, with as little resistance as possible, be able to rerun my code, be able to get exactly the same results as me, and then be able to build on it and extend upon it. And this rationale led me to the development in my PhD of a new piece of software called Q. So that meant that I needed to follow best practices in computational research. And there's a lot of references here which motivated me. So that meant that I was going to try and avoid manual data manipulation. So it means trying to write code to automate as much as I could. And that code needed to be readable, it needed to be accessible, it needed to be able to be tested using automated software testing and needed to be put under version control. Some of these references also refer to simulation models specifically, and for simulation models to be reproducible, it is said that they should be clear and readable, modular and extendable. So bringing all this together, I developed a new piece of software for doing discrete event simulations called Q. Now Q, C-I-W, is the Welsh word for a queue, Q-U-E-U-E. And I'm really proud of that name. And this is a open source Python library for running discrete event simulations of queuing systems. There's documentation and it's all available on GitHub. It's open source and it has a permissive license. So what that means is that it's free for you to download whenever you want. It's free for you to use for whatever you want. It's free for you to look at the source code. It's free for you to edit the source code. And it's really welcoming for you to push those edits back to us as contributions to the library. It's built in a really object-oriented way to try and keep in that modular theme. And the fact that it's object-oriented and within a Python ecosystem means that I hope this is really amenable to mixed methods modeling and be able to become part of something larger, such as optimization algorithms. Let's have a look at this in action. So I really want to show this library off. So here's a small queuing system. There are two nodes. So the first node, customers arrive, they wait to be served. There's one server. The arrival distribution is exponential. The service times are uniformly distributed, and there's infinite capacity. As many people as you want can wait at a time. After they leave that node, about 40% of all customers get routed to another node, node 2. This node also has its own arrivals, and they are deterministic. It has deterministic service times. There's 2 servers, but now there's only room for one person to wait. And what that means is when this is full, when this second node is full, arrivals from the outside get rejected, and any customer trying to enter node 2 from node 1 get blocked. And that's really important to my work. So they get blocked at node 1, they remain with their server, which means that server is not free to serve anywhere else until room becomes available at node 2 and everything gets flowing again. So I want to show that how Q can model this. So here I have, this is a Jupyter notebook and it's a way of running Python code. So I just want to show you the code for running that system. So the first thing I do is import the Q library, and I'm also going to import a data analysis package so we can manipulate the data. And the model which describes that system is a network object. And in order to define that, we take each node in turn and we list what is their arrival distribution. So the arrival distribution of the first node is exponential, the second node deterministic. The service distribution of the first node, the service distribution of the second node. The number of servers at each node, the capacity at each node. And then how are they connected together? They connect it together by a matrix of routing probabilities. So when they leave the first node to enter the second node with probability 0.4. So that defines the model. And then I want to run a simulation of that. So in order to do that, I can build a simulation engine, which takes in that object. I can run that engine for a certain amount of time units. Once that's run, I can take all the records from that, and the records look like this, which is just a record of everything that's happened during that simulation. And then I can use some manipulation of this data frame to get some KPIs. So for example, this is the average waiting time at each node. There is full documentation for this library online. And you can see that in this documentation, there are tutorials for how to use it. There are also a number of different guides on a lot of other features we've implemented into the library. So for example, these features include priority classes of customers, batch arrivals, time dependency, bulking behavior, and so on. In the paper where we introduce this library, we compare Q to a number of other simulation options, so including Simulate and AnyLogic and Excel. And we compare all these simulation options in terms of how amenable they are to reproducible research. So stuff like, can they be tested with an automated testing suite? Can they be put under version control? Are they readable and modular? And we think Q performs really well in terms of these sort of dimensions. That's what it was designed for. A slight drawback to that, however, is that, as you can see from this graph, Q is slightly slower to run than other simulation options. However, as you just saw, I don't think that really hinders its usability in any way. Right at the start then of the development of this library, the automated testing suite came in really useful. So the automated testing suite meant that whenever I was adding new features, I could make sure that those features weren't causing bugs in any of the existing features. And right at the start of the development of this library, this testing suite picked up a bug. And that bug was that the system I was modeling wasn't behaving in the way I expected it to behave. And I looked into this problem, and it took me a while to realize what was going on. But what I realized was there wasn't actually a bug at all, but the testing suite had picked up that the system wasn't behaving as I expected it to behave. And the reason was I'd come across a phenomenon which I hadn't expected. I'd come across a phenomenon I hadn't really heard about before called deadlock. Now here's a real world example of deadlock. This is a road system in gridlock. And you can see here that what's going on is these red cars are blocked from continuing their natural progression of movement due to the blue cars. The blue cars are blocked from continuing their natural progression of movement due to the yellow cars, who are blocked by the green cars, who are blocked by the red cars. So actually those red cars are indirectly blocking themselves. Those red cars are waiting for themselves to move in order to be able to move. That's what deadlock is. And a big part of my PhD thesis then was investigating this phenomenon. How does this occur in queuing networks? Well, imagine we had an example here. We have a 3-node network. They're all full, and they're all got, they haven't got infinite capacity, and they're all full. These 2 nodes have 2 servers. This node has 1 server. Now imagine the customer who's with a server B1 finishes service and wants to move to the top node. But the top node's full, so they get blocked. So this customer is waiting for people in this node to move before they themselves can move. And this can happen again and again. So for example, the customer at server C1 gets blocked, and so on and so on. Now there's a problem here because the top 2 nodes, you can see that all the customers in the top 2 nodes are waiting for someone to move. And they're actually waiting for themselves to move. These 2 top nodes are in deadlock. In a simulation of this, the simulation would just grind to a halt. No more events would happen until the end of the simulation. But this actually might be something which needs to happen and needs to be simulated. So in the real world, deadlocks might happen. And in order to break that deadlock, some external force would have to come in, realize what's going on, and break that deadlock in some way. Now, if you wanted to simulate this, in order to be able to trigger that deadlock resolution procedure, you'd need to know when the deadlock had happened during the simulation run. And that's a piece of work I worked on, was being able to detect when these deadlocks were happening during a simulation run. And in order to do that, I defined a directed graph which represented the states of that queuing system. So this directed graph, the vertices correspond to servers of the queuing system, and edges are going to correspond to blockage relationships. So for example, when the customer at server B1 is blocked to the top node, an edge is drawn between vertex B1 and every server of that top node, because they're waiting for one of those servers to become free. And we can carry on and carry on and carry on. And I proved that this directed graph can detect deadlock, because deadlock occurs if and only if that directed graph contains a knot, and a knot is a set of vertices which are inescapable by traversing the edges. I then managed to prove some other results around simplified graphs. So for example, in two-node networks, this simplified to just finding weakly connected components in the directed graph, and so on. Now, because I was developing Q at the time, and because of Q's modular and extendable nature, I was able to, as I was proving this stuff theoretically, I was able to put it into practice and actually detect these deadlocks in a simulation. And I want to show an example of that now. So here again is the Q software. I'm defining a network here. I've just got a two-node network, exponential arrivals on both the nodes, exponential services on both the nodes, two servers each, both of which are capacitated, and every possible routing probability is more than 0. So this can deadlock. And then when I build the simulation engine now, I can tell it, I want you to detect deadlock. How are you going to detect deadlock with this state diagram object, what I just described? And now I can simulate that system until it reaches deadlock, and it'll stop the simulation once deadlock is reached. And I can look at how long did it take to reach deadlock. And in this case, this system took 2.03 time units from an empty system until it reached deadlock. And that was because of this object which builds up that state diagram as it goes along. In the same paper, as proving that, we built some Markov models of some small queuing systems that we knew would deadlock. And here's a representation of one of those Markov models. I don't expect you to really analyze this. I'm only going through this quick. But one of the key features here was that the deadlocked states were modeled as absorbing states of the Markov chain. And it's plural, deadlock states, because there are different configurations you can have when you get into deadlock. But these are absorbing states, and that give insight straight away. That told me, because I know that Markov chains are guaranteed to reach their absorbing state, I know that if a deadlocking queuing system, if a queuing system can reach deadlock, it is guaranteed to reach deadlock. It's just a matter of time. And it could take a long, long time, but it's guaranteed to reach there eventually. So what I could do using both the simulation and these Markov models, with these Markov models, we can calculate the time, the expected time it takes to reach an absorbing state. And I looked at combining the two methods. I looked at investigating the effect of different parameters on the times to deadlock. And these are some of my favorite graphs. I really enjoy these graphs because they do say some quite interesting things. So in this graph, I'm showing that as the external arrival rate increases, you reach deadlock quicker. And that makes sense. You're filling up that queue quicker. Here, as we increase the queuing capacity, you slow down the time to deadlock. And that makes sense because you've got more capacity to try and fill up. Here, as you increase the number of servers, you increase the time to deadlock. So you slow down the time to deadlock, again, because there's more space to fill up, but it's also harder to reach deadlock because the condition of deadlock is all the servers are blocked. But this graph was really interesting. I really enjoy this graph because something's going on here. This graph, which is as I change the service rate, is not monotonic. And that's because services, and so the service rate, contribute to both getting rid of customers from the system and to feeding them back in and blocking customers, which causes deadlock. So this is not a monotonic increase or decrease. This is this bowl sort of shape. And that's because at different levels of service rate, the different effects take more priority than the others. So you've just seen there how extendable Q is. So Q is built in a way where that some brand new methodology was able to be implemented straight into the software as soon as we developed it. And a lot of my work after my PhD has involved trying to extend Q in some way. So I've been looking at those deadlock resolution methods and trying to build some optimization algorithms within Q so that we can find the best way of resolving those deadlocks. And with an MSc student this summer, I undertook a project where we looked at trying to model some hybrid simulation and in specifically discrete event simulation and system dynamics together using Q. So here's an example of one of the things we looked at. Here we've got a discrete event Q interacting bilaterally with a system dynamics environment. So a discrete and continuous models working together. And we managed to do this in Q because of its extendable nature. So how did we do this? We took the event scheduling approach that Q uses. The event scheduling approach is just a slight modification of the famous three-phase approach. So this is what Q uses natively, and we added an extra step in. So that extra step was after the A phase, which is when we move on the clock, we solve the SD component numerically for the time gap we just moved along. And then we sync up all the parameters before actually carrying out the events. This was possible because Q sits in a Python environment and there are some brilliant Python libraries for conducting scientific research, and the SciPy library has differential equation solvers that we can use to solve that SD component. I think I'm getting close to the end now. So on my last slide, I want to talk about some of the other applications of Q, which I haven't talked about, both what I've used Q for and what I know other people have been using Q for. So part of my PhD, I worked with a health board in Gwent in Southeast Wales, modeling the flow of elderly patients around a large healthcare system that incorporated both secondary care and community care services. The model was used to compare different scenarios, and those scenarios corresponded to different levels of rollout of a new preventative intervention for elderly people. And so we used Q to run those scenarios, and the results we got from those fed into further workforce planning models. And that paper now is under review. I've also, outside of my PhD, worked with other health boards where I've modeled cancer diagnostic services and critical care units using Q. But it's not just me. I know that Q is starting to build up a bit of a user base and a bit of a community. And one of the best emails I get, and I do get emails from users emailing me about their use of Q and what they're using it for. And it's really interesting to see the different things Q is being used for. So I've got this Venn diagram here because I feel like of all the stuff I've used it for and of all the stuff I know other people have used it for, all these applications fall somewhere into this Venn diagram. It's either been used for understanding a system, optimizing a system, communicating results and behaviors, or in education. So for example, in Cardiff, I know there are PhD students who've been using Q to model cancer services. Some have been using Q in conjunction with some game theoretic models to model ambulance blocking. And I know some people have been using Q in conjunction with some novel machine learning methods to assess healthcare need resources. Outside of Cardiff, I had correspondence with people who are using Q in Portugal for communicating behaviours around public service uses. I know some people have been using Q to model Internet of Things topologies and the communication within those topologies. And some people are implementing optimization algorithms in order to optimize 5G services. And the last one there is education. This is something I'm particularly passionate about. Q is being used in education, not just by me, but outside of Cardiff as well. But I can talk to you about what we are using Q for. Q is being used to teach simulation, but it's also being used to teach programming through the medium of simulation. And I think that's quite a neat application of Q too. So thank you all for your time, and thanks to the OR Society for giving me the opportunity to speak about all these things I'm really passionate about. Thank you.
Great, thanks very much, Geraint. Got a question from Mark Elder, so let me read that one out. Geraint, your talk is so interesting from several points of view. And his question, how to explain deadlock to a user? Deadlocks are obvious to us and fairly obvious in a diagrammatic form, but users just say, why is my model broken? It won't run. Any thoughts on how to explain them to users?
When you say deadlocks are obvious to us, I think they are when you explain them and when you can explain them diagrammatically, like you say. But they weren't obvious to me when I first started looking at them. Like I said, I thought there was a bug, and so I can see how users would think that too. So like I've shown today, diagrams are really helpful. When I started off as a PhD student, when I used to go to conferences, I talk about my work in coffee breaks, by showing that I couldn't eat a biscuit and hold two coffees at the same time because my hands were in deadlock, and stuff like that. But I don't know. I think the diagrams are one of the most useful ways of communicating what's going on here.
And I guess, in a sense, the beauty of the software here is highlighting that a deadlock could be a problem for them to investigate. It would identify when a system has gone into deadlock. Yeah,
definitely. And like I said, deadlock doesn't mean your system's broken or your model's broken. It could be exactly what needs to be happening, but you need to know that.
Yeah, great. Okay, just got an eye on the time. We've got no other questions at the moment. Just to let everybody know, obviously, if you have any queries or passing on to Geraint, we're more than happy to do that. So thanks very much, Geraint, and I'll hand back now to Edmund.
Thank you very much.
Thanks.
Thank you, Gavin, and thanks, Geraint, for such a fascinating talk. It really was interesting. Thank you. So I'm really delighted to be able to introduce this panel that is going to look at the outstanding work of Professor Ailsa Land. Ailsa was awarded what many consider to be the Operational Research Society's highest honour, the Beale Medal, in 2019. I don't want to repeat all the details of Ailsa's citation. You can read it in the online on the OR Society's website. But I will just say a few words. Ailsa pioneered work on branch and bound, and that's reshaped the landscape of mathematical programming, and the impact and the influence continues to this day. She was also one of the early pioneers of computational operational research, and over several decades, she has made outstanding contributions and a really high impact to the methodology and the practice of operational research in a wide variety of applied problem domains. In addition, she helped to establish an innovative 2-year diploma in operational research at London School of Economics for a graduate apprenticeship scheme set up by the British Iron and Steel Association. Later, as Professor of Operational Research, she supervised several master's students and PhD students who have gone on to achieve international distinction. Now, so I've already mentioned that this event is unique in being the Society's first online event, but it's also distinctive in being in having a panel rather than a traditional lecture. And the panel presentation and discussion that you're about to hear will focus on the impact of Ailsa's work in the field of optimization. I'm delighted to introduce to you Professor Doug Shier, who is Emeritus Professor in Mathematical and Statistical Sciences from Clemson University. Doug is chairing the panel this afternoon, and Doug will introduce the panel members to you. Over to you, Doug.
Thank you very much, Edmund. It's a pleasure to be here, and I'm just in awe of the panel that we have assembled here. Thanks for providing this introduction about the contributions of Ailsa while she was at London School of Economics and Political Science, and how, in fact, some of her pioneering work in Branch and Bound has had an effect that continues to this day. I'll just add to that, when I checked recently with Google Scholar, her publication together with Alison Doig is so heavily cited. It's like almost 3,700 citations to that particular work, continuing to this day. So as you've mentioned, this has definitely withstood the test of time. This is a contribution. And one other comment is that any serious software for OR, mathematical programming, will include branch and bound techniques. Our speakers will also show how, in fact, right now, branch and bound still lives well in terms of the interfaces with machine learning, artificial intelligence, and OR of the future. And I will emphasize that it wasn't only her contributions to branch and bound, but she's also sort of displayed this very unique economic lens that she loves to see things through, which is often a very unique perspective, and also a very geometric point of view that's sometimes quite different from your usual analytic equation point of view. I think overall, her contributions, and some of them are as diverse as classical network optimization, quadratic programming, and the traveling salesman problem, but other things more recently in data development analysis and sports analytics. So she has this wonderful ability to sort of seek out different corners in which optimization may be there hidden or not. As also mentioned, that she has really was at the forefront of what we now would call computational operational research. And her work with Susan Powell was to develop Fortran codes for not only mathematical programming problems and also discussing the appropriate data structures and test problems, but she extended this as well to things for the TSP and I believe also the data development and analysis, always making this freely available to anyone who wishes to make use of them. So her book, a 1973 book with Susan Powell, is also highly cited. Before I go on to the panel, I want to mention a couple of things. First of all, the fact of this breadth and mathematical programming applications is really a fitting tribute to Martin Beale, who was really one of the pioneers of mathematical programming and its practical use in the real world. And so this panel will give their perspectives about things going on in the real world and the impact of mathematical programming optimization and what lies ahead in terms of its future as well as its past. I will emphasize a couple of things. First of all, that afterwards there is a Q&A where you can pose your additional questions. And after the formal presentation with the slides ends, then the panel will be able to address those questions. Also, the panelists themselves provide a great diversity of backgrounds and wealth of knowledge in terms of their expertise and their perspectives. I also was mentioned that earlier to my colleagues here that they actually represent on the panel 7 different time zones. So we're literally going to see a span of time and diversity and viewpoints here. So thank you very much. And I'm going to now introduce our first panelist for this discussion, which in a way is talking about the past, the present, and the perspectives of mathematical programming. Our first speaker is Anna Nagurney. I'm so pleased that she's able to join the panel here. She's very highly sought after. She's written many, many books and articles, and is Professor, the John F. Smith Memorial Professor in Department of Operations and Information Management at the Eisenberg School of Management, which is at the University of Massachusetts here in the United States. She's also been she's a founding member of 2 different centers. One is a virtual center for super networks and a super networks laboratory for computation visualization. To indicate her breadth of interest, she's very much now a very highly sought out source in terms of supply chains and their fragility relative to the COVID-19 pandemic. So without much further ado, I'm going to let Anna take away and lead off this discussion, this wonderful panel discussion. Anna, up to you.
Thank you very much. It's wonderful to have such a brilliant introduction. I'm so deeply honored for the opportunity to be recognizing Dr. Elsa Land, a role model for all of us. The way I frame my presentation is to use actually direct quotes from her. I think we will all gain from her wonderful pearls of wisdom. Next slide, please. Would you believe that in July 2019, Professor Elsa Land was actually interviewed by a colleague from the London School of Economics, Dr. Laszlo Vake, as part of the Informs History and Tradition series on oral histories of luminaries. I had served on the Informs History and Traditions Committee for many, many years and had also argued that we need more females to be represented in this very important group of oral histories. And Dr. Land was actually the first female, so honored. I urge you to listen to the video and to also read the transcript at your nearest opportunity. And in her fantastic panoramic and very interesting interview, she notes, among other folks that had influenced her research, John Murchland. And do you believe the world of OR is just so wonderfully small and connected? I had actually cited the work of John Murchland, who brought the very important Bryce paradox in English to the world in my dissertation, and I have continued to cite him. And what is so special is that she recognized the seminar series at the London School of Economics and also the reciprocity associated with John Murchland, recognizing also the importance of networks and graph theory and cooperation when it came to computer programming and learning from one another, which I think is fabulous. Next slide, please. Now, just listen to these fantastic quotes, okay? And we can all learn from them. I cannot see that an objective function, which is just profit, makes any sort of sense of all. It's not the way a world should be run. Now, read this, okay, and absorb it. When it comes to the global pandemic, when it comes to disaster management, indeed, as we know in operations research, very often there are other criteria that we need to incorporate in decision-making. It's not just about profits. And moreover, another very important lesson for all of us, she said, and as you know, you have to publish. It's publish or perish, isn't it? Which I love, okay? And very important to finish your tasks. Said someone, I'm not going to mention the name, was very good at inventing new things, but didn't want to think anything through to the end and didn't publish. So make sure you finish your work and get it published. And now listen to this. According to Dr. Land, who said, but if you want my basic opinion about OR, is that it was great for wartime. Okay. Although we are not officially at war now, right? Various officials have stated that we are at war with the coronavirus. And I agree. Okay, the COVID-19 pandemic has spurred mobilization on an international scale not seen since World War II, 80 years ago, where we see the foundations of our fantastic discipline of operations research. OR played an essential role then, and again is engaged. We are all engaged in very intense scientific efforts with high stakes, trying to mitigate the pandemic, to help in response, and also in recovery. Next slide, please. Our profession has responded in such a substantive way. We have offered advice to governments, I know in the United Kingdom and other parts of the world, and also in the United States. And our work is actually impacting policy. We are working at a furious pace, fueled by adrenaline, but our work is making impact. Okay, and I think that's really, really important. I also would like to single out a sister society of the Operational Research Society, Informs, that has a special website which highlights very many researchers who've contributed to battling the coronavirus in terms of healthcare, supply chains, and even in terms of transportation security. And I also urge you to have a look at that, and you'll see the great work that's being done in cold chain vaccine logistics, supply chain network modeling. We heard from the previous speaker a bit on hospital capacity expansion, as well as many, many other areas. So again, this is in the spirit of Dr. Land's. We are making an impact. Next slide, please. And the research that we have done even pre-pandemic has been very multidisciplinary in nature. And a lot of the work has focused on perishable product supply chains. And these are also the supply chains that have been most adversely affected in the pandemic, from food to pharmaceuticals, to blood supply chains, and now the vaccine is also a perishable product. So the work is multidisciplinary, including contributions from chemistry and physics, and it shows kind of the history also of operations research, where we bring different communities together, different perspectives, to try and address some of the most challenging problems faced by our planet today. Next slide, please. Now, as we know, we're soon approaching the anniversary of the declaration by the World Health Organization of the pandemic, which occurred on March 11th, 2020. I had been monitoring the situation globally because we have many colleagues and collaborators around the globe. And I had been noticing that there were many shortcomings in terms of healthcare delivery and also major disruptions to the very important blood supply chain. Blood cannot be produced. It's something that has to be donated. On March 12th, the day after the World Health Organization actually declared the pandemic, I published an article on blood supply chains in The Conversation, which actually went viral. And shortly thereafter, Informs, in its Analytics Coronavirus Chronicles, asked me to expand upon my article. Next slide, please. Now, this is something I want to get across. It's not just critically important for us to be publishing in journals and to writing books. We have to get the news out about the work, the great work that our community does. And this is something I've been doing throughout the pandemic. On August 4th, I published another article in The Conversation because I was very, very upset about the relentless competition for PPEs nationally and also internationally. And then in addition, even before we had a vaccine approved, I was concerned about the ultra cold chain and the importance in terms of logistics associated with getting these very high valued vaccines, you know, from the origin nodes to the destination nodes. So since we had been doing work on that as well, I published another op-ed. Okay, and the conversation, which we have versions also in the United Kingdom, Australia, other parts of the world, there's no copyright associated with this. So once you write an article, it can be reproduced by many other media sources. So it's an excellent way of getting the news out. Next slide, please. And you see the news definitely got out. I was very involved with media, lots of interviews, radio, TV, all sorts, and also in the press. And that's something also important to do, which isn't easy to do because usually they want you like right away, but it's essential for our field. Okay, and also very gratifying because you can make a big impact. Next slide, please. And in fact, my article on the blood supply chain was cited on the first page of a very important memo signed by 22 attorneys general to the then head of the Department of Health and Human Services in the United States. And it in fact impacted policy. Okay, there was loosening in terms of the restrictions on blood donations because of shortages. This had a big impact, and I was very, very gratified and also very touched. Next slide, please. This is the memo. And next slide, please. It was signed by all these attorneys general. Next slide, please. And so let's listen to this, please. Okay, towards the end of our interview, okay, with Professor Vague, Professor Land says, but in terms of what I have achieved as a lifetime, have I left the world in any sense better by doing what I did? I think the answer is no. Might I have done better if I'd lived amongst the economists and had some effect there? I don't know. Okay, Professor Land, you have made an immense impact on the field of OR and on the practice of OR. And today, we all thank you and salute you. We will make sure that the contributions of those working in OR will continue to make positive difference. Thank you very much.
Oh, wonderful. Thank you so much, Anna. And I'm going to not take up any more time except to introduce our next speaker, Karla Hoffman, who I have great respect for. She is currently professor of systems engineering and operations research at George Mason here in the United States. And she's a past president of Informs, which Anna mentioned. It's the Institute of Operations Research and Management Sciences. She has not just been content to be in the classroom or to be doing research at her bench, so to speak, but she's interacted with a variety of government agencies and corporations on various OR applied problems. And most recently, I'd just like to mention, she's part of an award-winning team that worked on the Spectrum Incentive Auction for the U.S. Federal Communications Commission, which generated quite a substantial savings. So I'm going to now turn it over to Karla. Thank you very much.
Well, thank you, Doug, and thank you, Anna, for giving a wonderful background on Elsa Land and her work. I agree completely. First of all, I'd like to say it's an extraordinary honor to even talk about Elsa's work because I believe it has had an extraordinary impact on everything people do when they're modeling optimization, and especially optimization with any integer variables. This work is what we all stand on when we try to do that. Next slide, please. So, you know, Anna very nicely described the idea of branch and bound, and I looked up in Wikipedia how they defined branch and bound and liked it. So this is what I'm reading. The branch and bound algorithm depends on an efficient estimation of both the lower and the upper bounds of regions, branches of the search space. If no bounds are available, the algorithm degenerates to an exhaustive search. So the genius of branch and bound algorithm, I believe, and I do think it is genius work, is that it opened up large amounts of research in bounding. And if you think about what happened at the very beginning of certainly integer optimization, most of the algorithms were implicit enumeration, Gomery cuts, facet cuts, disjunctive programming, but it assumed that these cuts would be sufficient to solve the problem. And we quickly learned, primarily from the work in the traveling salesman problem, that that wasn't true. And that what you really needed to be able to do was to prove optimality, not by enumeration and not exclusively by cutting planes, but by the ability to get the lower bound equal to the upper bound. Now that might seem simple because it's a perfect concept of what you need for the proof of optimality, but it created this enormous amount of research that continues to this day on how we do bounding and also how we do tree search. That tree search is not just necessarily branching on a single variable, but there's row branching, there's logical branching. The whole field of constraint programming and decision diagrams is looking at that branching strategy differently than it was looked at the beginning of the thoughts on branch and bound. Today I want to highlight just how much work has gone on since Ilse's first work on branch and bound and how it all sits within this framework of bounding. Next slide, please. So bounding, especially in combinatorial optimization, requires improving the LP bound, or if one were using a Lagrangian relaxation, one is always using a relaxation as a bound. But that bound can be awful. And if that bound isn't good, we are not going to be able to solve the problem. And what has happened over the last, say, 50 years? Terrific pre-solve routines. Lots and lots of cutting plane routines. Looking at combinatorial Bender's decomposition. Thinking about just solving a subproblem that says your relaxation is wrong in this way. Keeping a variety of constraints around that you only use when you need. Getting this bound up is absolutely critical. And if you look at current commercial state-of-the-art codes, an enormous amount of work has gone into this improving the relaxation bound. Next slide, please. But that's not all. You need two bounds that work. And originally, branch and bound just waited to find a good solution within the tree. And the traveling salesman problem, I think, was the first that really said, we need a bound, and we need a good one, and we need it quickly, and didn't even use anything related to what they knew from the relaxation bound to get that. They used Lynn Kerningham's algorithm to find an upper bound. What's happening today in software? First of all, software creators have realized that users usually know about a lot about their problem, and they've put in all of these links to make it easy for the user to say, if you know something about a feasible solution, please tell me. And so there are MIP starts. There are, even if you don't know all of the variables that might be in an optimal solution, if you know some of them, please tell the code, it will help. And then there are lots and lots of heuristics built into the codes, and even links so that if you want to call a heuristic that has nothing to do with this package, that too is possible. So if you get a great feasible solution and you get a good bound, your tree search is going to work and you're going to be able to solve the problem. But without these bounds, this, it's complete enumeration, and that doesn't work. Next slide, please. What's happening now? I am really, really excited about our ability to move forward and look at the really hard problems. Look at global solutions to nonlinear integer optimization. And they go back here too. Again, we go back to the earliest work on global nonlinear optimization and using underestimating functions if you're minimizing or overestimating functions if you're maximizing to be able to bound the problem. It still requires the same concepts as branch and bound. Divide and conquer. Prove certain regions cannot provide the optimal solution. Branch on either regions or variables of interest. It's clearly not as well developed as integer optimization is, but we do need fast, general heuristics for nonlinear integer optimization. And we're beginning to see the same links in the nonlinear optimization codes and the nonlinear integer optimization codes that look very similar to what we see in a mixed integer optimization code. And I'm also very excited to see the computer science community really interested in the operations research community's understanding of nonlinear optimization to help their neural networks, to help them get the solutions they need. And when I talk about nonlinear integer optimization, I'm including within that stochastic optimization. So I am including the Bayesian networks that include the optimization. I'm thinking about stochastic optimization that is often being solved by integer optimization techniques. The whole world, this is what is so exciting to me, is that we're no longer siloing the optimization community into integer, linear, nonlinear, stochastic, as if they're all separate. The world is nonlinear. It has logical constraints. It has stochastic properties, and we're beginning to build out software that's capable of looking at these problems holistically. And the foundation for this is branch and bound. Next slide, please. So as Doug mentioned, I have always been interested in developing software, using software to solve hard, important problems. And as a consultant, I've thought, because Doug asked me to, what do you really need? First of all, to be successful, you need an advocate in the organization. It's classroom work unless there's a real problem that somebody cares and needs a solution to. And then you need the trust. One gets trust by listening and working to understand the goals, as well as the biases of the decision makers. It's hard often to teach students that we are not the decision makers, and that decision makers don't just want a single problem. They want to be able to make informed decisions. I believe OR does that well, but it's much easier to do if you're embedded in the organization and understand the thinking and the concerns of the decision maker. And also to be willing to do the background work, not only to build the fun modeling that we all love, but to do the routine jobs that need the data collection, the data cleaning, the listening to the problem, all of that. I think the new challenges for our community, and specifically optimization, is the gig economy. Suddenly, we are being asked not to solve, we are still being asked to solve the big, hard, important problems that might take a long time to get a solution to. But we're also being asked to solve problems in milliseconds or at most seconds. If you're thinking about Uber or FedEx or Amazon or whatever organization of that type you're thinking about, they need to make decisions in seconds. And as always, a timely solution is far better than a provably optimal solution provided months after they needed a solution. So my final lessons learned are: decision makers want understanding and not a single solution. And there are always things left out of our model. So we have to not only give the solution, but hear the response that the decision maker has to why they don't like the solution, and then revise the modeling so it is consistent with the world in which the decision maker lives. I want to thank Doug and the Operational Research Society for having this panel. I truly think it is a wonderful event, and it is an honor for me to be talking about ESSEC's research that was probably one of the inspirations while I was in graduate school. So thank you, Doug. And thank you, the Operational Research Society.
Oh, that's wonderful. Karla, thank you so much. It's really been sort of a real journey going from sort of the theory of branch and bound to modern day applications, which has sort of been mirrored in your own experience too. I will just mention sort of another piece of glue here is that historically, when the idea of branch and bound came about because of a problem that was provided by British Petroleum to these young researchers at the LSE, Elsa Land and Ellison Doig. So out of that particular need to include things which were discrete variables has now arisen this whole field. I'm happy to provide this transition in terms of applications and how you interface with clients. Jeffrey Camm, who's got a wealth of experience in terms of applications. He is currently Associate Dean of Business Analytics, as well as Inmar Presidential Chair in Analytics at Wake Forest University in the United States. He's also Executive Director of the Center for Analytics Impact at Wake Forest, and previously served as Editor-in-Chief for the journal Interfaces, in which you have to demonstrably show the impact of your research in practical situations. He has consulted himself for numerous organizations and corporations, Procter & Gamble, General Electric, Owens Corning, and he's got real insights to help us know what really makes a successful OR project. So I'm going to turn it over to Jeffrey. Thanks so much.
Thank you, Doug. Again, it's an honor to be on this panel with you today. I'm wondering, if not for Branch and Bound, what I would have been doing for the last 30 years. So thank you so much, Professor Land, for all of your work. And it's really an honor to be a part of this panel. I'm going to reinforce a lot of what Karla said just in previous discussion. And so we can go to the next slide, please. So I've been in academia since getting my PhD. My PhD is from Clemson University, so Doug and I have a connection. But that program, I literally took half of my classes in the math department and half of my classes in the business school. So it's very applied, very focused on solving problems. And then after I graduated, landed at the University of Cincinnati in Ohio in the US. And that department, it turned out, was very focused as well on interacting with industry. We had very strong researchers, but always tied to problems in industry. So I landed there as a young assistant professor. Publish or perish was certainly part of the culture, as we heard about before. So you had to do strong research, but you also had to be focused on problems in industry. And to some extent, the mentality was to be legitimate in the classroom, you had to have done work with companies. So that's where I landed there. And these are some of the companies I've worked with over the years. Now that, as Doug mentioned, I'm more into administration, so I've been consulting less, but I've learned a lot of lessons over the years consulting for some of these companies you see on the screen here. And all of it was mixed integer programming, every project. And you can see here, it might look like a strange mixture of organizations. Procter & Gamble, if you look down to the far right, it's a little bit difficult to see. That's a New South Wales Parks and Wildlife Service. So I've done everything from optimizing supply chains, which we've heard about, to trying to preserve biodiversity through nature reserve site selection and everything in between. And so as everybody knows, mixed integer programming is just applicable in so many different areas. But mostly I've been in supply chain optimization, and I want to focus in the center there is Procter & Gamble. Their headquarters is in Cincinnati, where I was as an assistant professor, and was lucky enough to be part of a team. They wanted to redesign their North American supply chain. So Mexico, Canada, United States, they had purchased, they had mergers and acquisitions. They knew their supply chain was very much overcapacitated, and they wanted to, in their words, rationalize the supply chain. They went to one of the highest end consulting companies in the world. This is 1990. And that consulting company said, we don't think we can solve that problem. You should talk to the military. And to tie it back to, again, Professor Land's notion that tying this all back to your being at war, luckily they came to the University of Cincinnati and asked us to try to tackle the problem with them. So redesigning the North American supply chain. And I'm going to tie many of the lessons I've learned. I was lucky enough to learn in that initial project with Procter & Gamble. So here's the situation. We decided, well, my first reaction as a young assistant professor was, let's build this model, be on a mainframe at the time, let's crank it out, let's get the answer. And right away, the response from Procter & Gamble was, no, we're not doing that. What we want you to do is build a system on a laptop that our product category teams can use, because we want them to have buy-in to any solution that we come up with. And we're going to let them interact with something you develop to develop a supply chain, that all comes together, and they will believe in it because they help construct it. So what we did was we broke the problem up from plant to distribution center, and from distribution center to customer zone. And the front end we could solve, using choices, actually build a laptop system with a geographic information system on it. And these category teams could choose different capacities, open and close plants by clicking on the map. And then a network optimization that was very fast would run the best shipment from product from plants to distribution centers. But we had broken the problem up in those two segments, plant to distribution center to customer zones. So the question was, well, assigning customer zones to distribution centers and choosing distribution centers as an integer program, and they're not going to want to sit there even if for a minute to let that run. They want this to be a very interactive system. So if we could go to the next slide, please. So tying it back again to what Karla just said, sometimes you have to have very fast solutions. And my colleague, Dennis Sweeney, said, Jeff, there's a paper I know about in the SciAm Journal of Applied Mathematics, and it's called Canonical Cuts to the Unit Hypercube. And Dennis Sweeney pointing me to that paper literally changed everything I've done since. So if you're not familiar with this work, I recommend you go read it, but it's a beautiful piece of work. You stay within branch and bound, you add a cut The only point that gets cut off is the previous solution. What does that do for you? It allows you to generate a family of solutions, in fact, a rank ordered set of solutions, or generate alternative optima when they exist. So the way we got that laptop system to be in real time is I took that network and generated a family of solutions, like the top 25 solutions in terms of going from distribution center to customer zones. And that became a table lookup and an enumeration through that table. And the product category teams were able to interact in real time with the geographic information system. They had a big summit after that of all the product category teams. They had a lot of conversation about how should we merge these independent supply chains together. They arrived at a solution. They tested it with integer programming like I originally wanted to with a big model. It was close enough. They simulated on top of that to look at risk, and they arrived at a solution. So two big lessons for me in that project. One is this idea that you can generate family of solutions within branch and bound very easily by putting things in a loop. And the other is that you have to pay attention to what management wants, and buy-in is really important if you care about implementation. That project saved Procter & Gamble $250 million a year in North America, and they later rolled that system out into Europe and Asia. So I learned a lot from that, and it had a big impact on me going forward. So next slide, please. So 5 years later, I'm on another project for a company. It's in healthcare space. Manufacturing is in the US. They ship product to Europe. They wanted to redesign their European distribution network. And so you can think of a typical network optimization. We're choosing distribution sites. The plants are fixed. That's coming from the US. And what we're really after is service to the customer zones, and we want to minimize cost. We did some optimization, mixed integer programming, arrived at the fact, did that trade-off curve with variable cost, looked for the elbow in the curve as you increase the number of distribution centers. Looked like 5 was the right number of distribution centers. And then we decided to do a little investigation with cuts to the unit hypercube. After finding a solution, we had a solution in hand, had 2 current DCs and 3 new DCs. So in the solution that was truly optimal, there were 2 distribution centers from their current network that have to shut down 3 and open up 3 new ones. Applied a cut to the unit hypercube and found out that the second best solution had 4 of their current DCs in it, and it was suboptimal by only 0.4%. And so by looking at the second best solution, we found a much better implementable solution because our math program did not have transition cost in it. And so lesson learned early on from Procter & Gamble, I've applied virtually to every project I've done since then. I never rely on a solution. I always generate a family of solutions, and then we start talking to management and look at trade-offs. So to reinforce, again, something Karla said, management is not looking for an answer. We need the engine. We need to know how to get that answer, but then we need to provide a family of solutions. Next slide, please. So again, reinforcing previous discussion, black boxes do not work. And sometimes when we're using sophisticated machinery like branch and bound and integer programming, in fact, an answer is really hard to explain. We're hearing a lot now about explainable AI. Explainable OR is also a challenge. And so what I've learned there over the years is sometimes, in fact, the most valuable recommendations are so counterintuitive, they're very difficult to explain. But if you benchmark, managers will listen to benchmarking arguments. So I spent a lot of time over the years building optimization models, taking what a client is doing now and locking it down in my model, benchmarking that, and then trying to show how at least we think if we operate according to the solution we're recommending, what the difference might be. In essence, always treat a project as if you're being paid by the impact. That forces you to document the impact the best you can with the models you have before you even implement anything. Next slide, please. So lessons learned. So now, when I teach, I spend a fair amount of time. In fact, I'm getting ready to teach a class in optimization in 3 weeks. I spend a fair amount of time in my class on optimization, teaching students how to find suboptimal solutions, because this idea of family of solutions is so valuable. Managers want alternatives. Explainable solutions. I spend a lot of time on benchmarking and how you need to convince management that they should implement what you're recommending. And so you need to know how to influence. We have a Master of Science in Business Analytics inside the business school at Wake Forest. And we have a wonderful course called Visual Analytics and Influencing, required of every student. How do you argue for the client implementing what you're recommending? And then lastly, I want to say, I think, and Anna and Karla both alluded to this, and I agree 100%. Given everything that's going on, there's an increased request I'm seeing in resilient solutions. So think about supply chains, food supply chains because of COVID. And so again, generating family of solutions, subjecting them to risk analysis is going to be more important, and tying it back to profit not being necessarily the most relevant objective. I think we're going to see a lot more of that. Don't give me the cost minimizing solution, because we know that's risky almost by definition. There's a bottleneck. And so instead generate resilient solutions. So thank you again for the opportunity to be on this panel. I am truly honored, and thank you again, Professor Land, for your seminal work in Branch and Bound. It enabled me to focus on modeling and having so much fun the last 30 years. Thank you. Thank you, Doug.
Jeffrey, thanks a lot. I really appreciate it. I think our audience will appreciate all those insights, hard won by experience. So thanks very much. We're now going to move on to Susara van Heever, who's director of IBM Expert Labs. And she has herself a passion for combining data, mathematics, and engineering to help people and businesses be more efficient, save time, manage resources, and even make better environmental choices. She's got a career that spans a number of industries, manufacturing, utilities, financial services. And within those, she's served in various roles, consultant, doing R&D, project management, and sales. Notably, she received an IBM Research Division Award for her work on smarter cities. Definitely a current and important area. And she's also an Open Group certified distinguished data scientist. Her work has impacted many industries, for example, in energy scheduling, telecommunications, and design of cities. So I look forward to hearing what Susara has to add to this wonderful conversation already. Thank you.
Thank you so much, Doug. And it is such a pleasure to be here today. So I want to thank you for the opportunity to join this group. And for Dr. Land, I actually never met you, but you had a huge impact on my life, both professionally and personally. So I'd just like to introduce that way. If we could go to the next slide, please. How I actually got very excited about the field of optimization. It started in my undergrad. I studied chemical engineering. And at the time, we were given this assignment to design a really efficient heat exchanger. And there are many different variables around type of fluid, type of temperature, the length of pipes, the diameter of pipes, you name it, the decisions get exponential very quickly. At the time, the only tool we had was simulation. So as students, we sat through an entire weekend running simulation after simulation until we got a good design. The next year, I started my PhD studies at Carnegie Mellon University. And I was given the same assignment by Ignacio Grossman. And he said, this time you guys use optimization. So we wrote a model that was maybe 10 lines of code. We pressed a little button that said solve, and poof, out popped this perfect solution. And I thought it was magic, and I never turned back. I ended up completing my PhD in the field, and in the next 20 or so years applied optimization, and especially branch and bound and MIP across just about every industry. Now, in the case of this design, it was actually an MI-NLP problem where we decomposed the problem into a MIP and an NLP, and we had this iterative algorithm that converged on the optimal solution. So that's in the professional sense. In the private sense, in that same time in my life, I attended integer programming class where I learned the details of branch and bound from Egon Ballas. And I noticed this handsome Swedish guy sitting next to me, and he ended up being my husband. And very shortly after, we had 2 wonderful children. So thank you, Elsa. The branch and bound led to a long career. I saw so many contributions of branch and bound across so many domains. And it also led to my family being what it is today. Now, this is not just me. If we go to the next slide, we know that branch and bound has had a massive impact across the world. If we look at the Edelman finalists from the Informs competition, and we look at the past years, let's say 30 years of winners, and you start reading those papers, and I have gone and I've read all those papers, you'll see that the financial contribution adds up to more than $200 billion over the years. So it's massive financially, but also in the way we run this world. Now, what struck me as soon as I got out of PhD school was that where optimization is really the heart of decision-making applications, a heart only functions well when it is surrounded by a body and working well within the body. So next slide, please. And so what I learned really quickly is that having my optimization model is great, but I need to understand that full linkage from understanding the data, getting the data in place, visualizing that data, using it potentially for predictions, for simulations of scenarios, getting to my optimization model, which can then recommend actions, plans, schedules, and then eventually today in the world towards AI, putting that in a system that can learn, reason, and adapt in this cyclical fashion. And so what I think, when I think of what makes OR truly successful in the real world, it is understanding that we as OR experts, yes, we're the heart, but we are part of this bigger ecosystem to bring a successful solution to the world. And I'd like to just illustrate this with a quick example. Next slide, please. This is a project that we did for Nedbank. It's a bank in South Africa. And you know that sometimes you'll go to the bank, you put your card in the ATM, and the bank spits it out, or there's no money, or there's no printer, or something's wrong. And when that happens, you as a client, you're frustrated, you might go somewhere else. And the bank actually, it's a big problem for them. They lose money that way. And so we went to Nedbank and we wanted to convince them to use optimization to solve this problem, to be able to do optimal maintenance. But we knew it might be a challenge. So we had to take a step back and think, how does our business user think at Nedbank and what's going to convince them? And so on the next slide, we started with, next slide, please. We started with thinking, just tell them what they can do with the data they have available today. And so we built them a dashboard. This is not a slide, it's an actual running dashboard. You can do something like this pretty easily with Shiny. And we said, with what you know today, you know what's going on in your ATM network, but you really don't know what could happen in the future or what to do about it. And so next slide, please. The first step was then to say, let's bring in machine learning, which was at the time the hot topic. So it was hard to start with optimization. And we say, okay, machine learning, what can we do for you? We can help you predict with some probability what could go wrong in your network in the next few days. But it's not going to tell you how to actually address that in the best possible way. This is where you need to look at optimization. And so next slide, please. The next thing we built a optimization problem, which, as you can see, we visualized in this. It was we could give the business user a URL to go play with this output to say, based on now the predicted issues in the ATM network, how should the maintenance crew for the day drive around the city to fix these problems? And we showed them by playing with different objectives. One objective we used was minimize the drive time. Let's say your drivers are trying not to drive so much. The other objective was minimize your revenue loss. And we put this in the hand of the stakeholder, the business, and said, see what happens, how math can really give you a very different outcome. And on the next slide, the final part to really seal a deal was scenario comparison. So on the left-hand side, we said, keep running your business as usual. That red block is the amount of money you will lose. Then we got to the middle and we said, sure, optimize, but use the wrong objective in this case, which was minimize drive time. Yeah, you lose less money and your driver's happy. And then finally, we got to optimize based on the right objective. And this was then the best result. And what for me was the most telling, a business user who had never heard of optimization before in their life, after this project said that they are going to use optimization in every single business problem they're going to solve from then on. And so this would be the takeaway, is really embed your optimization in a way the business understands. Next slide, please. And so, we can extend this to so many domains. A few years back, as I say, machine learning really got all the attention. And a good way to open that conversation was, well, machine learning is often used to predict something. Why are you predicting something? You're doing that because you're trying to make a decision. And optimization can help you make that decision in a better way across nearly all business functions. Now, this is not only on the business level. If we go on the next slide, we also know that optimization is often used in machine learning algorithms, from something as simple as support vector machine to some of the more recent innovations Karla talked about in deep learning and so forth. And then on the next slide, machine learning also can help optimization algorithms. So we know that is, for example, quite often used these days to be able to learn better strategies within branch and bound algorithms. And so here's just a few references. I can especially recommend the sources there by Andrea Lodi in the bottom. He has really a great presentation on how these work together really well. And so I would like to just get back to, on the next slide, get back to the big picture again. I know this slide looks incredibly busy, but what I want to highlight, what typically as a researcher or as a, let's say in my world, the pre-sales would do, is that middle block. You connect data, you analyze, you build a model, you train it, you visualize, and you evaluate. And the significant here is really, again, that is the heart, but the body needs to be thought of around that. So everything to the left, the data ops. So how are you going to manage the data? How are you going to make sure it's trusted? How are you going to share it in a way that you can run your models when they need to be run? Going back further, how do you scope the problem? How do you decide which problem you need to solve? Are you solving the right problem? Are you expressing the results in a way that makes sense to the business? Are you designing the architecture to be able to handle your model once you deploy it in the real world? And then if we go to the right of the slide, of course, once you have your POC that works well, you need to deploy it in a QA environment, in a production environment, and you need to make sure that model is trusted. And so this is where the explainability comes in, the scenario comparison, and you need to be able to explain to the business why that model made the decisions it did. And so here the context is, keep in mind, as optimization, we are part of this much bigger picture, and the better and earlier we work together, the better the outcome is. then on a final slide, please. Thank you. So I would like to end with just some pretty straightforward best practices to bring optimization success to the real world. And you'll notice none of this really talks about math. And that was one of my hardest lessons straight out of PhD was the math. Yes, it's important, but if it's only that, then you're not going to have the real world impact. You really need to look at this bigger ecosystem. So the first column there is all about how do you engage the business, catch their attention with something that's a quick win that shows value, communicate with dashboards, not slides, with dashboards that actually show the results in their language. Make sure you use business metrics like, I don't know, profit, efficiency, time savings, and be sure you know how you're going to collect and organize the data that you're going to need to make this a reality once you get beyond toy data, right, or experimental data. Make sure you have that long-term view in place. The middle there is something I often tell my clients is invest in the right team from the start. So make sure from the start your optimization people are talking to the data engineers, the IT engineers, the business audience. The second point there, invest in top talent. We all know optimization is a complex field, and the better your talent there is, the better you're going to do. And then finally, they're building the trust with the business owners. On the right-hand side is all about the technology. Sometimes an out-of-the-box solver is going to solve your problem perfectly. You don't need to do anything complex. Other times you're going to need something complex. And so the point there is use the right technology for the right problem. The second point there on Agile is to deliver a demo to your business user. And when I say demo, I mean a dashboard every 2 weeks. The dashboard has to, you have your underlying model and algorithm, but your dashboard surfaces the results. And the reason for every 2 weeks is that you need to keep that cadence going and get your results out. And then finally, the two last points, just getting back to the theme of what I talked about, plan ahead for your full life cycle. Don't wait until your POC is done before you ask for help or ask for resources, because then you could get stuck in POC limbo. Thanks again for the opportunity to speak here. And I think the next speaker is going to get into a lot more detail on ML versus optimization versus AI. So thank you, Doug. Thanks to all.
Susara, thank you so much. That was a great perspective. And I like the idea of this sort of full body perspective with all of these parts working together, but the heart alone cannot sustain the body. We need the arteries, we need the infrastructure. So thank you. And before we go to our final speaker to wrap this up, I want to encourage the audience to put some ideas there in the Q&A, because we will have some time after our last speaker, Ivana Ljubic, has her presentation, which again is going to impinge on artificial intelligence and its role here. Ivana is professor of operations research at ESSEC Business School of Paris, and also an academic director of this joint ESSEC and Mannheim EMBA. She's past president of the Inform's Telecommunications and Networks Analysis section, served on many editorial boards of journals, and her research in optimization has found quite a number of applications, various areas in telecommunications, network design, bioinformatics, and she has consulted for major telecom operators, both in France and in Austria. So I look forward to hearing from Ivana Ljubic. Thank you so much. And this will be our final speaker, and then we will welcome your input as people who are viewing this. Thanks.
Thank you very much, Doug, for this nice introduction, and of course for the invitation to be part of this panel. This is absolutely a great honor to be part of the panel, and a great honor to honor Elsa Land, to have this opportunity to discuss her achievements with respect to branch and bound, and also to look into the future of branch and bound and the overall research of mathematical optimization at the first place, discrete optimization. So I also have to say that branch and bound is part of my life for at least the last 20 years, and that I'm spending hours and hours together with my PhD students and with my colleagues, just by looking in front of my screen how the lower bound is getting closer to the upper bound, by looking at the branching nodes of the general purpose solvers being Cplex or Gurobi or Skip, just to mention a few of them. So when Doug invited me to participate in this panel, and when he mentioned that the topics should be spread between past, present, and future of AI, I thought really I would like to discuss something which is bothering me for quite some time, and this is this question, which you can see in front of the screen. Is or are AI? Is it or not? And we have a lot of academic discussions with our colleagues, and this is a question that is really dividing our community, I would say, because there will be people who will openly embrace it and say, yes, of course it is, and then there will be the others who are totally reluctant and who will say, no, AI is something completely different. Next slide, please. So before we start this discussion, what is AI? This is a major question. And you can find millions of definitions, and each one of us has some understanding about this. But this is my favorite definition, which is given by Larry Tesler, who unfortunately passed away recently, and who said AI is whatever hasn't been done yet. Well, from the perspective of the computer scientist, and when you look at the history of AI, this is definitely a definition which is sustainable and which will stay also for the years to come, right? And this is the definition that I like the most, because it also tells us that whenever we achieve certain advances in the computer science, then this becomes a mainstream, and the very next frontier, this is what we will consider as an AI. So the purpose of my presentation, of course, is not to give you the full opinions, but rather to trigger a discussion on this question that we can continue after my presentation. So then I thought, okay, why not asking Google? So let's see what Google is saying if I ask for the AI taxonomy. So next slide, please. And in Google, this is one of the most prevalent figures that you can find for the AI taxonomy. And I really don't know the true origin. I'm just providing you here one of the sources. You can find many blogs, many articles citing this picture. And in this picture, what is framed here in red is planning, scheduling, and optimization as part of AI. And so this is something that we may discuss. Do we really agree with that or not? Because clearly planning, scheduling, and optimization is exactly what we are doing in operations research. Next slide, please. Then just a few weeks ago, I found this very interesting and exciting article, which has been published in ORMS Today. Article by Michael Watson, who is practitioner with a PhD in operations research and management sciences. And what he says is, Inform does AI. And he says why artificial intelligence is the best term to describe what our members do. And he provides plenty of arguments, but the most interesting part of his story for me is the beginning, when he says in the end of 90s, when he just finished his PhD, he was involved in many academic discussions, whether what he was doing was operations research or management science. And then when he left academia and started working for companies, he realized that companies couldn't care less about the branding. What is the real name of this research? They care about the solutions. They care about, can you provide something which is useful for them or not? And then later on, we saw the emergence, the rise of the term business analytics. And business analytics is something that we all embrace today, and we divide it into predictive, prescriptive, the descriptive analytics, and so on. And we say OR is actually part of what we would describe as prescriptive analytics today. And now there is a new term, which is AI. So should we embrace it or not? This is the question. I leave it for you to think about that. Next slide, please. So when I teach my students, the students in the Master of Data Science and Business Analytics, but also the students of Executive MBA, I like to show them this slide because I say then for the data-driven decision making, what we need is AI and business analytics. So I put these two together because for most of the people, AI is actually machine learning, and this is just a part of the predictive part. Sometimes I also use the term AI-powered analytics to emphasize that we need both. But of course, personally, I like to have the word analytics still going on. And the students love it because of the idea that using the data-driven decision-making, they can mute the hippos. The point is, next slide, please, that the AI hype that we are facing right now is real, and it's really everywhere. And so what I'm showing you here on this slide, on the right-hand side, is a recent tweet from Hannah Fry. And OR members from the UK know her very well, I guess, because she's running a very popular BBC show, popularizing mathematics in the UK. And she discovered this article, which has been published in many newspapers, which is based on the research by Wang and Kosinski from 2018. They're psychologists who published in the Journal of Personality and Social Psychology results stating that they have been able to train a deep neural network by just in such a way that by just looking into a single photo of a person, they can say whether this person is straight or not. And the accuracy of their approach was 81%. And that was super exciting. The newspaper were reporting about that until Hannah realized the following fact. Actually, if you look into the statistics of the UK population, according to the recent results from 2018, more than 94% of the population are actually identifying themselves as straight, which means that without any super fancy deep neural network technology, just by labeling every single person, every single photo as straight, you will achieve an accuracy of almost 95%. And so the overall conclusion is, are we sometimes using neural networks and AIs as a hammer to kill a fly, as a sledgehammer to crack a nut? Is it maybe an overkill for the methods, for the approaches, for the applications that we might need? And her conclusion is not only that, but also that if the data is new gold, then we are living in the Wild West. We are surrounded by extraordinary claims, often with little proof that the algorithms can do or will do what they say. And so some work, but don't work well, and others are nothing but the snake oil. And this is something that hurts us, of course, because we are also people who develop serious algorithms and we care about this hype. And the question is, if we let others developing algorithms without understanding the mechanisms behind, what will happen in the future? Next slide, please. So the future is not so pessimistic, and there are some very interesting events going on and some bridges that are trying to connect the AI and operations research. And I'm just here showcasing one of the very recent examples. This is one of the top conferences in AI, which is Triple AI conference, on which our colleagues have organized a workshop about machine learning and combinatorial optimization. So combinatorial optimization is certainly a part of both worlds, of the world of AI and OR. And as even, let's say, a few decades ago, combinatorial optimization was at the foundation of the SAT-based algorithms. But in the last 10, 15 years, we see that the trends are moving more towards the deep neural networks. So the question is, how can we save our discipline and how can we actually combine the two worlds in the best possible way? Next slide, please. In this workshop, which is available online and you can access the videos, and I invite you to watch them carefully, one of the beautiful presentations was given by Maxime Gass, and this is where I would again like to honor Elsa Land, because what we can see here is that the world of developing new techniques for branch and bound is not sleeping. We can see, if you pay closer attention to the dates of these references, which are mentioned here, most of them are only several years old. So most of them are between 2018 and 2021. And most of these techniques, which have been cited here on this slide, are actually machine learning techniques which are used to fine-tune branch and bound algorithms. And they go from the finding the right, learning how to select the next node in the branching, learning how to select next variable on which to branch, which cutting planes to use, how to use primal heuristics, or the diving heuristics. So in terms of trends, we can say that something like 15 years ago, we have seen the world of exact algorithms and heuristics algorithms approaching each other. So the two communities approaching each other, and we have seen the development of what is known today as MIP heuristics or MAD heuristics. And some famous examples are local branching, proximity search, Rins heuristic, and so on. So that was 15 years ago. Now we see new trends emerging, and these trends are how can we exploit the power of machine learning to improve the performance of branch and bound methods. Next slide, please. Then I would also like to draw your attention to these lectures by Dimitri Bertsekas, which are now online available, in which Bertsekas also draws a connection between AI and reinforcement learning in particular, and the dynamic programming and control theory. And basically, in his words, what he's saying is, well, these two worlds are very much the same. We are only using different terminology to express the same things. So next slide, please. So the question is now, where do we see the future of OR? So a few years ago, in 2016, that was one of the pioneering articles using reinforcement learning to solve the traveling salesman problem. So the TSP is, of course, a holy grail of combinatorial optimization. And a lot of people from our community were upset to see that the papers are being published in which neural networks and reinforcement learning are used to solve TSP instances with 100 nodes. Why are we upset? Well, because we know very well that there is a software called Concord, which can now solve instances with, let's say, Bill Cook just announced recently that he can find almost optimal solutions for making a TSP tour visiting more than 2 million stars in the universe. Next slide, please. And then very recently, on the 18th of February, this is where I, through the tweet of Bill Cook, learned about the new challenge, which has been announced by Amazon and MIT. And there is also a prize, which is $100,000 for what? So on the left side, you can read what is this challenge about. So Amazon is going to provide to the participants tours which are driven by the drivers in order to allow them to train the data and to try to beat the traditional OR methods. So the contest is seeking to produce solutions to the root sequencing problem that outperform traditional optimization-driven OR methods in terms of solution quality and computational cost. And then we may ask ourselves, but why? Why, if we on one hand have a solver which can deal not with 100 data points, but with hundreds of thousands of them and solve them even heuristically to very, very small gaps, if not optimally, why would we need now machine learning and deep learning techniques to approach this problem? Why should we use so much of computational power to train these networks? And as you can see, for example, from the comments on the top down on the right from one of our colleagues, Eduardo. He says the challenge statement starts badly because maybe ML community really wants to keep this myth, which is the introductory part of every single AI and machine learning paper, which says the problem is NP hard and therefore it is untractable and therefore we have to look for machine learning AI-based methods. So this is a stereotype, and where do I see now the disruption coming, or let's say the threat coming from all these recent developments? Well, the point is that the ML and AI community is, in terms of numbers, much bigger than the OR community. So, but just by the law of big numbers, what can happen is that some of our state-of-the-art results, some of our state-of-the-art algorithms remain completely unnoticed by these let's call it in general computer science community, and that then some other algorithms which are clearly underperforming become more widely adopted and more popular than ours. So the question is, are we risking to become an exotic discipline which will be completely thrown away by these recent AI trends or not? So on the bottom left corner, you can see that at the same time, while Amazon and MIT are running this challenge on AI for routing problems, we also have a traditional DIMEX challenge on the vehicle routing problems. So the future will show which one will remain more relevant for the industries, for the organizations. And of course, the next question would be, can we actually draw the benefits from both worlds by combining them together? So to conclude, what I believe should be the measures that we should take as a society or as a community. Next slide, please. Here are some thoughts, some ideas. First of all, I believe that in the AI and the CS community, our results have to gain more visibility, because a lot of researchers wouldn't know about the state-of-the-art algorithms. We have very often situations in which exact methods are actually outperforming state-of-the-art heuristics. Second, we should probably forget about these endless academic discussions about branding and how do we call what we are working, but rather care about the solutions. Then what is definitely needed is a knowledge transfer. And this workshop on machine learning for combinatorial optimization is an excellent example. Because what is needed is that we include OR researchers in the program committees of the computer science conferences and vice versa, and to organize different types of symposia, workshops, and tutorials. And then also, to avoid that these two worlds are not completely split apart, if we talk about business schools who have to embrace today more and more researchers working in data science, machine learning, and AI, well, then clearly the standard journal ranking lists that are used for hiring and tenure decisions at the business school have to be revised in order to include also the top computer science conferences. But on the other hand, if we want all our researchers to be part of this CS world, also the engineering schools have to embrace or to make similar changes in their policies. And finally, I want to mention as an excellent example, Ivana Labs from Montreal, which are employing researchers from both worlds, from machine learning and optimization, and working closely with companies. And this is something that I hope we will be able to see around the world, and especially in Europe in the next future. Thank you very much for your attention.
Ivana, thank you so very much. You've sort of brought us to the frontier of what we know right now. We started with a great historical preview by Anna, and we've worked through consulting all the way through here. We have a number of questions that I'd like to just, from the Q&A, I'd like to pose here. We may not be able to get through all of them, but here is one. mention was made, this is for Karla Hoffman, mention was made of the radio spectrum auctions. Can you say more about what are some of the latest issues in this regard?
Sure. I've been extraordinarily lucky to have been placed as a consultant in the FCC many years ago for a problem that didn't work out, which was to do combinatorial auctions. And the industry basically refused that idea because they wanted more control of the auction itself. Since then, OR has been part of the thinking. We work with the economists, we work with the technological engineers, and auctions have flourished of various types within the FCC. But more importantly, as analytics has been playing a bigger role in decision making, we have been part of the group that has what eventually happened was at the FCC, there is now a Office of Economics and Analytics that the prior chairman founded to be sure that analysis is part of all of policy decisions. I'm very proud of that. I think it happened because we spent a lot of time talking to the economists, and the FCC allowed us to talk to the industry. So when a government agency decides to try to change regulation, they have to go out to the industry and see what the industry thinks about these regulations. And we had the opportunity to work through the issues not only from the government's perspective, but from an industry's perspective. And I think there was a question about how do you get industry or within a corporation the concepts of what you're trying to do. And I think the question is really, how do you get to understand what the goals and the competing goals of the participants are, and then figure out a way forward that shows that you have heard the concerns and the goals and put that as part of your modeling. It might be a constraint. It might be part of the objective function. It might be an analysis afterwards that just says, you're really worried about this, but our optimization has actually improved your goal, whether it was implicitly or explicitly. But I think it's the interactions and the communication that makes a successful project.
Great, thank you, Karla. I've got a question here where definitely the recording will be available on the OR Society website eventually, but someone had asked whether or not that they could actually obtain the slides themselves. And I will check with the panelists offline about this rather than putting them on the spot right now. I'm pretty sure that we can, but let me go ahead and check with them just to make sure there isn't anything proprietary that would be compromised there. A couple more questions. I have quite a few here, but one from Gautam Appa: can anyone recommend an easy to use and free to run optimization software for helping to provide alternative solutions? He wishes to get a college in India that he's connected with to start using it. So again, maybe the thing to do is if someone can say, yes, there is, or to send it to me, and then I can go ahead and send links to Gautam for that. So just keep that in mind, panelists, and go ahead and you can contact me and I will try to forward that on. Bob Scott says, often difficult problems to model are accompanied by political dimensions, which are even more tricky to incorporate and arrive at implementation. Any insights about dealing with these messy situations? Well, let me leave that open. Probably, I think everyone here might have a good story, especially Jeff and Karla, but go ahead.
Sure. Can you hear me?
Yes, yes.
Oh, okay. Yeah, that was the whole point of my first example. Was we probably could have solved the problem to optimality in one big model, but politically, P&G knew that there would be so much resistance if we came in with an answer that they decided to have the product category teams be a part of the process, and recognizing that they were probably going to give up some efficiency in the solution. But the political side of things was so strong, they just felt like getting managers involved in the process was the best thing to do.
Thank you. Let me take one other question here, a more technical question, directed towards our last panelist particular, probably. Can we say that the latest AlphaFold algorithm for solving the protein folding problem, that's really an important problem in bioinformatics, is the first instance where AI methods outperform OR methods? Any thoughts about this from panelists?
Maybe I can answer this question. So maybe it's not even the first one. Maybe there are some other problems where OR methods are already outperformed, but we are not aware because they are not so famous. But this is exactly the point, whether we are in a very critical phase as a community right now. And the question is, are we going to be disrupted by the new AI technologies, and are we going to survive it? Because we have 70 years of research that we have invested into developing very specific methods. And we say that Concord, for example, contains more than 700 different functions. It's very sophisticated solver, right? On the other hand, these deep neural network approaches, they require maybe a few hundreds of lines of code to be implemented. And the question is, are we going to survive this disruption or not?
I'd like to add one quick thing there. Is I don't have a great understanding, but some of these massive deep learning networks require literally billions of elements and estimation that in itself, without the great advantages of very fast computers and massive storage, would not have been possible before.
Yes, but we are now at this turning point where it is possible.
Mm-hmm.
I would like to also add something to that. I think it's important to recognize in the era of climate change, the impact of emissions generated through, for example, neural networks and machine learning. We've had studies done at UMass Amherst, actually, that went viral, identifying the impact on climate change by training these various neural networks, and they are immense, okay, essentially equivalent to multiple cars over their lifetimes for just training, one fairly basic algorithm. So, if we can solve to optimality and not have such, extensive requirements in terms of energy consumption, I think that's another kind of twist, which is a plus for our community.
I believe that someone else had mentioned earlier, and I lost the post there, that are there opportunities to approach our climate change crisis with using tools from optimization and OR? Maybe that would be our last question, because I don't want to keep people from their networking opportunity. Mm-hmm. Any thoughts from folks about that opportunities in the climate mitigation and analysis?
Yeah, I have some thoughts there. So that area is absolutely ripe for OR. We know that today already many of the utilities will use OR models to optimally balance between renewable energies and traditional energies in a way that matches supply and demand and takes care of the uncertainty. Things like maintenance. Wind farms are super expensive, actually. So how do we optimally maintain them? Think about how to deal with the uncertainty to do that, the weather conditions, the ocean, etc. And then recently I saw a really great example of beach cleanup. So how do the powers that invest in that actually decide where's the worst hit areas, and how are they going to invest in crews or volunteer activities to go do that beach cleanup? So yeah, I think the possibilities are endless.
Well, thank you. I want to thank these panelists. Clearly, this has been a very stimulating discussion, and further questions, I'm sure you can send them to me or the panelists, or I can get you in touch with them. Thanks very much. I also want, on a personal level, I want to thank Gautam Appa, my good friend and colleague, for helping to conceptualize and make this panel come into fruition, as well as Frank Land. And sort of in closing, thank you, Elsa. Your sphere of influence is being felt today. Thanks very much. And I will turn this back over to our chair. Thanks very much, Edmund.
Thanks very much, Doug. Definitely on the closing stretch now. Doug and other speakers have mentioned the fact that there's a networking session that's going to be taking place right after this. That's taking place on a separate Zoom link. We've shared that link through the chat functionality. I think it's been emailed to you too. So please do take advantage of that and join in with the networking opportunities afterwards. And then just to close this out, I'll hand back to Edmund for some closing words. Thanks.
Thanks, Gavin. And look, I think this has been such an interesting event. It's been outstanding. It really has. I've very much enjoyed it. I would like to thank everybody involved. I'd like to thank Geraint for opening up with such a great talk. To thank Elsa for her outstanding contribution to operational research. I'd like to thank Doug for chairing so well, and on all the panel for such fascinating presentations. Such a coherent panel, but so wide-ranging too. It really was outstanding. Thank you all very, very much indeed. I really also want to extend my thanks to the OR Society staff for putting this event on, to Gavin and the team, particularly to Hannah Wells. I have said on many occasions that the way that the Society has responded to the pandemic and been able to put on events like this, that we'd normally all be in London at the Royal Society, but you know, the way that the Society has done this is outstanding, and I'm very, very grateful to the staff for such a good job of this event and of all the events that we've held since the opening of the pandemic. And finally, I'd like to thank the audience. Thank you all for your questions and for contributing to such a great Beale Lecture, a unique and distinctive Beale Lecture in the history of the Society, but a really, really outstanding one. So thanks everyone, thanks for attending, and goodbye.